So the first thing I want to show you then is a very simple demonstration of the photoelectric effect. So you can see the equipment I'm using. In the middle there, that is an electroscope. An electroscope is basically a piece of equipment that you would use to measure and detect charge. To the top of the electroscope, I've added a metal plate. That's just a piece of zinc that I've attached to the top there. To the left of the electroscope, there is a metal cylinder. That is an ultraviolet lamp. I'll also be using a torch in this as well. First thing I'm going to do is I'm going to charge up the metal plate using an EHT. So when I charge up the plate, what I'm doing is I'm adding lots of electrons to it, so it becomes negatively charged, and you can see there that the gold leaf has become repelled from the stem that it's attached to, indicating that it's become charged. Now, interestingly, I can discharge the electroscope using an ultraviolet lamp. So the ultraviolet lamp is shining onto the zinc, and you can see that I've discharged the electroscope and the gold leaf has returned to its original position. So that would indicate then that I'm knocking electrons from the zinc using ultraviolet light. Now, interestingly, if I try the same thing again, so I've just charged it up again there, if I try the same thing again using visible light, nothing happens. It doesn't work with visible light, at least for zinc. So even if I shine a brighter lamp on it, it still has no effect at all. Only ultraviolet light is able to do this. Okay, so ultraviolet light is able to knock those electrons off and discharge the electroscope. And this proves something quite significant. This actually proves that light behaves like a particle, and I'll explain that in the next section of the video. Okay, so what's actually happening then? So you notice when I shine my ultraviolet light onto the zinc plate, like so, you saw that the electroscope was discharged, or the zinc was discharged. Okay, well, this is because the ultraviolet light has enough energy to liberate some electrons from the surface of the zinc. So actually these electrons will pop off from the zinc, they will be ejected or liberated from the surface, and they will leave the metal and it will discharge the metal. Okay, we call these photoelectrons. So electrons ejected in this manner are called photoelectrons. Okay, but how does this then prove that light is behaving like a particle and not like a wave? Well, you notice that when I tried to eject some photoelectrons using visible light, I couldn't do it. Nothing happened. Okay, the plate remained charged. So this doesn't work with visible light. If light behaved like a wave, then you would expect that you could just increase the energy of the wave, in other words, make the light brighter, and you'd then eject the photoelectrons because you'd then give the electrons enough energy to escape the metal. But that doesn't happen. It only works with ultraviolet light. And it doesn't matter how bright the ultraviolet light is either. I can just shine ultraviolet light. As long as it's above a certain energy or above a certain frequency, I can eject photoelectrons. Okay, but it doesn't work with visible light, for zinc at least. Why is this then? So light, this is sort of saying that light is behaving kind of like a particle here. And I'm going to introduce you to the word photon, which is what we call a particle of light. So a photon, that is a particle of light, okay, and it behaves kind of like a packet of energy. Okay, so a photon is like a packet of energy, it's a particle of light, and it's important to know that a photon cannot donate part of its energy. It has to donate all of its energy or none of its energy at all to the electron. Okay, so this is what a photon is. It's a particle of light. Now these particles of light are coming in, they impact the zinc, they might give an electron enough energy to escape the zinc. If they didn't have enough energy, if that packet of energy wasn't big enough, then the electrons wouldn't be able to escape, no matter how many of these packets of energy are hitting it. Like if you increase the brightness, you just have more packets, but that doesn't matter. Each individual packet can only donate all of its energy or none of its energy. So if it's not high enough, then the electron won't be able to get enough energy to escape. So this is the key proof then that light is behaving like a particle or like a photon. Okay, so how do we then work out the energy that one individual photon has? So the energy of a photon can be given using this equation here. So the energy of a photon, E, is equal to h. Now h is something called the Planck's constant, and we times it by the frequency of the light. Okay, so the energy of the light is tied to its frequency here, okay, by a constant called Planck's constant. Planck's constant is very, very small. It's equal to 6.63 times 10 to the power of minus 34 joule seconds. Okay, so a really tiny number. So each individual photon has a very small amount of energy. Now, if that energy is high enough, it can liberate photoelectrons. Now, the minimum amount of energy required to liberate a photoelectron is given by something called the work function. Now, the work function of a metal determines the absolute minimum amount of energy that a photon needs in order to liberate a photoelectron. And we represent it with this symbol here, okay? And this is called the work function. Okay, it's given in joules and it represents the minimum amount of energy a photon needs to liberate a photoelectron. Okay, and that work function is unique to each metal as well. Okay, so it's specific on the metal, it depends on the metal. Some have a high work function, some have a lower work function. Okay, now these photoelectrons have enough energy to escape because the energy of a photon of ultraviolet light is higher than the work function. And then whatever's left over is going to go into the kinetic energy of the photoelectron. In other words, it will move away. Okay, how then can we work out the energy that the photoelectron has? Well, we can do this. Okay, so if we take the energy of the photon, HF, okay, that energy of the photon is going to be absorbed by an electron. Okay, now the electron needs to use some of that energy to escape, so we subtract the work function, and then whatever's left over will go into the kinetic energy of the photoelectron. Now this is the absolute maximum amount of energy that a photoelectron can have, so we're going to call this max, or EK max. Okay, only the electrons at the very, very surface of the metal are going to have the maximum amount. Other electrons might have some energy as well. But it will be less than that if it's come from deeper within the metal. This is only the electrons at the very surface. Now you can work out the velocity quite easily of the photoelectrons by using the equation as well. So subtract the work function and then sub in half mv squared. Okay, and this is V max. Okay, that is the energy of the this term here is the energy of the kinetic energy of the photoelectrons. Okay, and that is the basics of the photoelectric effect. Okay,